This discussion centers on a paper titled Galactic Gravitational Field Measurements, Black Hole Energy Transfer, authored by Christopher Young. The paper proposes a novel mathematical framework to understand how black holes transfer energy into an entity termed the auxiliary modulation coordinate. This work challenges conventional views of black holes as terminal gravitational singularities, suggesting instead that they act as dimensional interfaces, converting matter into structured energy patterns that preserve quantum information. The analysis leverages entropy-resolved resonance profiles and an extended gravitational metric incorporating field modulation, aiming to resolve long-standing paradoxes in black hole physics and unify concepts of matter, energy, space, time, and consciousness under a generalized modulation-based field equation. To ground the discussion, the paper introduces foundational concepts central to the framework. The auxiliary modulation coordinate is a structured, modulating energy field existing parallel to spacetime, encoding energy dynamics, quantum behavior, and field interactions as wave-based resonance patterns. It is not a speculative hidden dimension, but a computable field structure derived from resonance collapse and energy modulation, with components representing quantum waveforms, field curvature, energy propagation, and temporal modulation. Complementing this is the entropy-resolved resonance profile, a non-iterative mathematical framework that collapses complex field interactions into single-step harmonic solutions. This method avoids iterative procedures by applying entropy modulation and universal harmonic weighting, providing a fundamentally new computational approach based on energy resonance. The introduction outlines the black hole information paradox as a primary motivation. Traditional models treat black holes as terminal singularities with event horizons that trap all matter and information, leading to unresolved conflicts between quantum mechanics and general relativity. This paper reconceptualizes black holes as energy processing systems interfacing with the auxiliary modulation coordinate, converting matter into structured energy patterns that propagate through this coordinate while preserving quantum information. By applying entropy-resolved resonance profiles to an extended gravitational metric, a modified Schwarzschild metric incorporating field modulation, the paper demonstrates mathematically how energy transitions from observable spacetime into the auxiliary modulation coordinate, identifying resonance channels and mechanisms, maintaining quantum coherence across dimensional boundaries. The framework extends foundational theories in quantum field theory, information theory, and non-local field dynamics into new mathematical domains, positing black holes as computational nodes in a universal information processing network, linking energy, information, and consciousness. The mathematical foundation is established through the extended gravitational metric incorporating auxiliary modulation coordinate effects. This metric modifies the classical Schwarzschild solution by adding a coupling function dependent on the auxiliary modulation coordinate, transforming the event horizon from an absolute boundary into a dimensional interface, allowing bidirectional energy and information flow. At the critical radius corresponding to the Schwarzschild radius, the coupling function balances the spacetime metric terms to avoid singularities, forming a dimensional gateway between spacetime and the auxiliary modulation coordinate. Analysis using entropy-resolved resonance profiles reveals that field equations at this resonance point behave analogously to quantum critical phase transitions with scale-invariant correlation functions, suggesting the event horizon functions as a phase transition boundary in reality's fabric. Furthermore, the metric creates a temporal resonance chamber at the horizon where information can be stored in temporal oscillation patterns before transferring to the auxiliary modulation coordinate, enabling information escape through higher dimensional channels. The tensor analysis extends Einstein's field equations by introducing an auxiliary modulation coordinate correction tensor, accounting for energy contributions from this coordinate. This correction preserves diffeomorphism invariance while coupling spacetime curvature to higher dimensional modulation structures. The modified Riemann curvature tensor near the event horizon includes non-local contributions from the auxiliary modulation coordinate, effectively creating wormhole-like connections that allow information to escape the black hole interior via higher dimensional pathways. A significant contribution of the framework is the resolution of classical singularities. By incorporating auxiliary modulation coordinate effects, the extended gravitational metric remains well-defined even as the radial coordinate approaches zero. The coupling function's dominant terms near the singularity ensure the metric components remain finite, interpreting the classical singularity as a transition point where energy flows from spacetime into the auxiliary modulation coordinate. This approach differs from loop quantum gravity and string theory by maintaining continuous geometry and identifying the singularity as an artifact of insufficient dimensionality. Moreover, it addresses instabilities at the inner horizon by stabilizing the interior structure through energy transfer into the auxiliary modulation coordinate, preventing infinite density states. At the event horizon, quantum field dynamics become critical for energy transfer. The quantum field equations resemble the Klein-Gordon equation with an added auxiliary modulation coordinate coupling term, enabling energy and information transfer across the horizon. The use of modified tortoise coordinates incorporating auxiliary modulation coordinate corrections alters causal structures near the horizon, rendering it traversable through higher dimensional pathways. The effective potential governing quantum fields includes modulation coupling terms that create tunneling pathways, with resonant modes facilitating energy transfer into the auxiliary modulation coordinate. Quantum tunneling mechanisms are advanced by modifying the action integral to include the coupling function, producing tunneling probabilities with frequency-dependent modulations. This results in non-thermal radiation spectra carrying information about the matter forming the black hole, preserving quantum information. For charged particles, the tunneling probability generalizes the Schwinger mechanism to include auxiliary modulation coordinate effects, creating correlated particle pairs where one escapes as Hawking radiation and the other encodes information in modulation patterns. This transforms the event horizon from an absolute barrier into a selective membrane permeable to information. Hawking radiation itself is fundamentally modified, with the temperature adjusted by an auxiliary modulation coordinate function dependent on the modulation state. This leads to deviations from the purely thermal spectrum predicted by conventional theory, introducing information-carrying correlations in the radiation. The radiation spectrum includes gray-body factors, incorporating modulation effects, encoding quantum information about the black hole's formation. The total entanglement entropy between outgoing radiation and auxiliary modulation coordinate patterns matches the Bekenstein-Hawking entropy, ensuring information conservation throughout black hole evolution and resolving the information paradox without requiring abrupt transitions. The paper then explores matter capture and energy extraction processes. The effective potential governing particle trajectories includes modulation coupling, modifying capture cross-sections, and creating time-dependent variations in accretion efficiency. The classical Bondi-Hoyle-Littleton accretion rate is adjusted by modulation factors, explaining observed variability in black hole systems not accounted for by environmental changes. Auxiliary modulation coordinate coupling enhances relativistic jet production by creating coherent energy channels aligned with black hole rotation, increasing jet collimation and efficiency beyond conventional models. Accretion energetics are modified as gravitational potential energy converts to kinetic and thermal energy within the accretion disk. The energy release per unit mass incorporates modulation coupling, altering energy distribution and creating distinctive spectral signatures. The innermost stable circular orbit radius shifts depending on the modulation state, affecting the inner edge of the accretion disk and the high-energy spectral cutoff. Accretion efficiency, the fraction of rest mass energy converted to radiation, is enhanced by energy channeled into the auxiliary modulation coordinate, explaining super-Eddington luminosities without modifying radiative transfer physics. Energy partitioning includes radiation, black hole growth, relativistic jets, and auxiliary modulation coordinate injection. The latter accounts for discrepancies in observed energy balances, especially in smaller, rapidly rotating black holes, which couple more strongly to the modulation coordinate. Energy injection mechanisms into the auxiliary modulation coordinate include direct quantum tunneling at the event horizon, resonant extraction via frame-dragging effects creating modulation patterns, and vacuum polarization, where virtual particle pairs transfer energy into modulation patterns. These mechanisms ensure efficient energy transfer from accreting matter into the auxiliary modulation coordinate, contributing to information processing and storage rather than increasing singularity density. The dimensional transition of energy at the event horizon is formulated through a modified path integral including coupling Lagrangian terms that connect spacetime fields and modulation dynamics. This phase transition boundary is characterized by an order parameter satisfying a free energy functional with a double well potential, analogous to second-order phase transitions in condensed matter physics. The transition exhibits critical exponents matching the three-dimensional Ising model, suggesting universality. Topological defects in the order parameter field create protected information channels analogous to Majorana zero modes, enabling information flow across the horizon. Quantum field injection mechanisms further include vacuum polarization with auxiliary modulation coordinate contributions, non-local field couplings enabling entanglement and energy transfer across the horizon, and topological phase transitions creating stable coherent structures encoding topological information. These structures, similar to solitons or skyrmions but existing in combined spacetime modulation manifolds, provide robust information storage protected against perturbations, addressing fundamental issues in information preservation. Information encoding in the auxiliary modulation coordinate is formalized through a density matrix representation of modulation patterns, with entropy balance equations extending previous models to account for modulation coordinate contributions and correlation terms. The encoding decomposes into modulation basis states spanning spherical harmonics, radial functions, and modulation functions, with coefficients containing complete quantum information of infalling matter. The information capacity grows with the effective dimension of modulation space, exceeding bounds set by conventional spacetime alone, providing a mathematically rigorous solution to the black hole information paradox and unifying quantum mechanics with general relativity. Within the auxiliary modulation coordinate, four fundamental force structures govern information processing. First, an information flow and coherent stabilization force organizes quantum information flow across modulation dimensions and time, conserving information and compressing patterns akin to algorithmic complexity and quantum error correction. This force ensures coherent propagation and efficient storage of information. Second, a baseline resonance stabilizer provides a carrier frequency foundation, dynamically adapting to energy inflows to maintain field stability through self-regulating homeostatic mechanisms. This resonance connects to fundamental constants, including the Planck length and fine structure constant, synchronizing processes in modulation space. Third, a rotational modulation force encodes angular momentum and spin structures, creating topological vortices with quantized winding numbers that store information indefinitely. These vortices correspond to geometric patterns in modulation space, preserving rotational information and coupling to extended gravitational effects, suggesting experimental tests via frame-dragging measurements. Fourth, localized quantum structures form stable soliton-like wave packets in modulation space with fractal properties, enabling hierarchical information storage with high capacity. These structures distribute information efficiently while maintaining locality resembling holographic storage systems. Together, these forces create a sophisticated universal information processing system driven by black hole energy inputs, converting matter into structured energy patterns, preserving and processing information on cosmic scales. Energy transformation in the auxiliary modulation coordinate unfolds through three phases. Initially, coherence establishment organizes incoming energy into coherent modulation patterns within roughly 10 Schwarzschild radii, following non-Markovian dynamics preserving memory of initial states. The coherence function exhibits eigenvalue distributions transitioning from Wigner semicircle to Marchenko-Pastor laws, indicating developing correlations. This phase consumes about 20 to 30% of incoming energy. Next, modulation pattern development spans from 10 to 1,000 Schwarzschild radii, involving diffusion and potential terms in a Schrödinger-like evolution equation. modulation harmonics self-organize toward critical states, maximizing information processing capacity, following maximum entropy production principles. Energy cascades across harmonics resemble turbulent cascades with Kolmogorov scaling, linking modulation dynamics to universal complex system behaviors. Finally, stable configuration harmonics emerge, characterized by harmonic temporal frequencies and resilient to perturbations through topological protection and nonlinear dispersive balance. These stable patterns maintain long-term information storage and cosmic coherence, forming a universal computational substrate continuously energized by black holes. The framework predicts observational implications and avenues for experimental verification. Black hole thermodynamics are modified, with Hawking temperature adjusted by modulation functions leading to non-thermal radiation spectra carrying internal state information. Correlation functions in radiation differ from conventional expectations, with analog black hole systems providing feasible test beds. The entropy-area relationship adjusts to include modulation entropy, preserving generalized second-law thermodynamics and affecting gravitational wave ringdown frequencies, potentially detectable by future observatories like LISA. Event Horizon Telescope observations offer further verification pathways. Predicted polarization patterns around photon rings include modulation contributions, potentially explaining complex polarization asymmetries already observed in M87. Radiation spectra near horizons should exhibit characteristic modulation-induced frequency variations. Time-dependent oscillations in black hole shadow and photon ring structures linked to modulation eigenfunctions could be detected via long-term monitoring. Information preservation tests focus on detecting subtle correlations in Hawking radiation predicted by the modulation framework but absent in standard models. Experimental proposals include entanglement harvesting near horizons, quantum echo detection following perturbations, and correlation measurements in analog black hole systems like Bose-Einstein condensates and nonlinear optical media. These approaches offer challenging but feasible paths to empirically test the predicted information encoding mechanisms. Mathematically, the extended gravitational metric and generalized modulation-based field equation form complementary descriptions linked through a mapping operator involving non-local kernels and curvature terms. This duality resembles gauge gravity correspondences and holographic principles, embedding conventional physical laws as low-energy projections of more fundamental modulation dynamics. Entropy-resolved resonance profiles provide computational tools enabling direct, non-iterative calculation of complex black hole configurations, overcoming limitations of numerical relativity near event horizons. The weighting operators derived from entropy considerations allow extraction of final energy states efficiently, facilitating analysis of black hole energy transfer into the auxiliary modulation coordinate. In summary, this paper advances a comprehensive mathematical and physical framework reconceptualizing black holes as dimensional interfaces, transferring matter into structured energy patterns within an auxiliary modulation coordinate. Through rigorous analysis, employing entropy-resolved resonance profiles and an extended gravitational metric, it resolves classical singularities, preserves quantum information, modifies black hole thermodynamics, and establishes black holes as integral nodes in a universal cosmic information processing system. The framework offers testable predictions across observational and experimental platforms, providing a unified bridge between quantum mechanics and general relativity, and deepening our understanding of reality's fundamental informational substrate.